Hey everyone, in this video I want to go over the mathematics of Egyptian fractions. So let's begin by talking about the definition of an Egyptian fraction. An Egyptian fraction is defined as a finite sum of distinct unit fractions. A unit fraction in turn is defined as a fraction with a 1 on the numerator, and you're going to have an integer on the denominator. So any rational number a over b, any positive rational number, can be written out or decomposed as an Egyptian fraction. Any value a over b with a and b being positive integers could be written out as a sum of unit fractions of the type 1 over n1 plus 1 over n2 plus 1 over n3 as an example, where n1, n2, n3 are all distinct. So they have to be different values. They can't be equal to each other. So this type of decomposition of any rational number a over b is known as an Egyptian fraction. So as an example, the rational number 5 over 6, if we wanted to write that out as an Egyptian fraction, that would be equal to equivalently 1/2 plus 1/3. So this is an Egyptian fraction because it's a finite sum of two distinct unit fractions. 1/2 is different than 1/3, and they're both unit fractions. This type of representation of rational numbers, or this representation of fractions in this way, was utilized a lot by ancient Egyptians, and there are writing examples from ancient Egypt that use fractions or that mention fractions in this format, so that's why they were given the name Egyptian fractions. This is not usually the way fractions are represented or taught in mathematics in schools nowadays, but this was the representation that was most utilized during ancient Egypt. And we know this mostly from a papyrus called the Rhind Mathematical Papyrus, which comes from the Second Intermediate period of ancient Egypt. And this is an example of the mathematical papyrus. It's currently part of the British Museum. It has different algebra and geometry problems. And then on the back, it had a Egyptian fraction table. And it has a couple examples of rational numbers and their Egyptian fraction decomposition. So I actually tried for quite some time to find a picture of the section of the papyrus that actually talks about Egyptian fractions, and I could never quite figure out what section it was, and I couldn't find a good picture, but I do have a replica and a translation of what I think the section on Egyptian fractions had in the papyrus. So it actually has a front side and a back side to the papyrus. So the recto, or the back side of the papyrus, was found to have a mathematical table, almost like a multiplication table, but instead of multiplication, it had Egyptian fractions on it. So this is the translated version of the Egyptian fraction table in the back of the papyrus. And when people looked at this, they found that this was a 2 to the n table. Assuming this is the correct portion of the Egyptian fraction table, this would be read as being the n in the denominator of the rational number, and then these would be the denominators for the unit fractions. So using this first one as an example, 2 over 5 could be represented as an Egyptian fraction 1 over 3 plus 1 over 15. So this was present on the papyrus, and if you do the math, 2 over 5 is equal to 0.4, and 1 over 3 plus 1 over 15 is also equal to 0.4. Same thing with, for example, 87. That is saying that 2 over 87 is equivalently equal to 1 over 58 plus 1 over 174. So this was a portion of the papyrus that had a 2 to the n table. So this shows that this type of representation of rational numbers was very commonly used, and it was so commonly used that they needed a table, or it was useful to create a table to refer to simple sums of Egyptian fractions. Interestingly about Egyptian fractions is that we still don't know how exactly did the Egyptians know these solutions. So how did they know that 2 over 5 is equal to 1 over 3 plus 1 over 15? Technically, we know that they do know it because we have the solutions that they wrote down, but they never wrote down the method or the algorithm that they used to get these results. So it's not quite clear how did they know that this information was true, or how did they come to the result of these numbers. And this information was not written down formally as a process or as an algorithm until a couple hundred years later, and it was first discussed formally. The method for getting Egyptian fractions was formally discussed by Fibonacci. Fibonacci in his writings mentioned multiple methods of calculating Egyptian fractions. The most common method that you're going to hear about is known as the greedy algorithm. And so this was one of the methods that was discussed in his book. And it's a very simple algorithm to find Egyptian fractions. And it has basically two steps that can be repeated. So in the first step, for any rational number a over b, any positive rational, you're going to find the largest unit fraction 1 over n, such that 1 over n is less than or equal to a over b. This is equivalent to searching for the ceiling of b over a. You're going to take that 1 over n and subtract it from a over b to get a new fraction. If the fraction has any remainder, so if it's anything other than 0, you're going to repeat steps 1 and 2 until you get that the final subtraction is equal to 0. So we can do this as an example. So let's use the greedy algorithm to solve this simple problem of 5 over 8, and let's try to find a solution using Egyptian fractions. In the first step, we need to find the largest 1 over n, such that 1 over n is less than or equal to 5 over 8. The way I would think about it for a simple number like this is that our unit fraction options going from largest to smallest would be 1/2, 1/3, 1/4, 1/5, etc. And 5 over 8 is greater than 1/2 because 1/2 would be 4 over 8. So I know that my first 1 over n could be equal to 1 over 2. Formally, choosing the largest n, like we said, that would be the ceiling of b over a. So in this case, that would be the ceiling of 8 over 5, which again would give you 2. So we're going to start with 1/2. So for step 1, we're going to take 5 over 8, which is our a over b, and subtract 1 over n, which in our case is 1 over 2. And that's going to give us 1 over 8 left over. This solution is pretty simple because the remainder that we have is itself a unit fraction, and it's different from our first unit fraction. So 1 over 8 is a unit fraction, and it's different from 1 over 2. So in the second step, technically, because we have a remainder, we would pick our next largest unit fraction, which would be 1 over 8. And 1 over 8 minus 1 over 8 gives you 0, and we're done with the algorithm. So our final solution for 5 over 8 is going to be equal to 1/2 plus 1 over 8. And this would be our solution using the greedy algorithm. So this type of decomposition or finding the finite sum of a rational number, this was used, for example, in ancient Egypt, or it's still a common way of finding how to split something equally. So let's say you have, just as an example, 5 pounds of grain, and you have to divide it equally among 8 people. Or let's say you have 5 pizzas, and you have to divide it equally among 8 people. This solution is saying that everyone can have half of a pizza plus 1/8 of a slice of the final pizza. And so this was actually a way that you can still do these types of problems that you might give kids in like elementary school of figuring out a way to divide things equally. And we know from ancient Egyptian writings that they used this for dividing grain, dividing plots of land, for example, after the Nile flooded, into equal parts. And so that's one possible use for this type of algorithm. So I just learned about this recently because I've been really into ancient Egypt, so it got me inspired to make a video about it. I was going to do another example using the greedy algorithm, but I think it's kind of simple and basic enough that people understand. So I'm going to end the video here, and thank you all for watching.